Hey everyone! So, in this video, I will be outlining the primary stages of stellar evolution, both for low mass and high mass stars, as well as some of the major conditions and properties of each stage. All right, so first off, we know where stars come from, right? They come from giant interstellar clouds of gas and dust, which we know as a nebula. So let's put that right there. I'm going to put it off to the side, such that we can start with a protostar on top here. And so as the nebula contracts, it gets denser and denser and hotter, and then eventually a protostar forms at the center of it, or at least at the center of the densest pockets of it. And if you wait even longer, the protostar continues to contract and heat up until its core gets hot enough to begin nuclear fusion, right? So the protostar then becomes, well, a main sequence star. So I'm going to now split it off into over here. We'll call this, if that protostar has greater than about 8 solar masses, m sub s is mass of our sun, then it becomes a blue main sequence star. All right, and this is also known as a high mass star, effectively. If that protostar has less than about 8 solar masses, so less than 8 m sun, then it becomes, either a yellow or a red main sequence star. So this is what our sun is, a yellow main sequence star. Now, in both of these cases, right, for greater than 8 and less than 8 solar masses, so all stars, initially they undergo the proton-proton chain when they're on the main sequence. And so again, this is the process that hydrogen fuses into helium, all right? And so all stars do this initially. It just so happens that the higher mass stars, so the blue ones, do this a lot faster than the lower mass stars, like our sun. But they all do it initially. And they also spend a vast majority of their time on the main sequence doing this. So something of like 90% of their lifetime is on the main sequence. So I'll put that also right there. Now, what happens next? Well, in the core of these stars, hydrogen is fusing into helium. Well, that means helium is being created. The core, though, is not yet hot enough to fuse helium into carbon. So what happens is that the helium just kind of collects at the very center. Remember, helium is a little bit bigger and more massive. The atom of helium is more massive than hydrogen, so it falls to the center and just kind of builds up. That pushes the hydrogen fusion to a layer around this helium core, this helium ash. And so eventually, when you get enough helium, the hydrogen is pushed out of the core. And when that happens, the star is now considered a red giant. So let's see. Let's go for the low mass first. And now it is a red giant star. Actually, to give me more room, let me shorten this arrow just a little bit. So this is the next primary stage for the evolution. So it's in blue. The high mass stars do this as well. Again, they do it a lot faster, but they still become a red giant, just like low mass stars do. Okay, so in this initial red giant phase, some characteristics are common to both. Specifically, they're getting brighter and brighter, so their luminosities are increasing. They're physically getting larger, so their radius is increasing too, and their surface temperatures, T, are decreasing. The surfaces are getting cooler, and that's why they're becoming more and more red or more orange. The blue ones become more orange and red, and the yellow stars and red stars become even redder. Okay? Now, this is, again, of the surfaces. So this here, this combination of properties is for the surface of the stars. What's happening inside, their cores are actually shrinking. Cores shrink and they get hotter. So the star itself, the star physically gets larger, right? Thus it becomes brighter, but their surfaces cool off. Meanwhile, their cores get smaller, get more dense, and thus become hotter. And so, thankfully, they become hotter because eventually, if they get hot enough, they're going to fuse helium into carbon. In fact, that happens when it gets to be roughly 100 million Kelvin, and that incurs the helium flash. So that's when we know that carbon is now being created. Specifically, helium, He, into C, carbon. So all of these characteristics are happening for both high mass and low mass red giants. All right. So the low mass stars, the yellow and red, what were main sequence stars, after they do this, they don't have enough mass to continue to get hot enough to burn carbon into heavier types of elements. So, like our sun will eventually make carbon, but that's it. And so eventually, it'll become now a white dwarf surrounded by a planetary nebula. And the white dwarf part will, or is, the core, or what was once the core of the star. The core will become the white dwarf. It'll continue to shrink, the density will continue to increase, and the gravities will continue to get absolutely enormous. Okay? It'll become a white dwarf. And then the outer layers of that star will just kind of puff out and fizzle out and become the planetary nebula. All right? So this is the end result for a low mass star, like our sun. For high mass stars, this red giant phase will continue, right? After carbon's created, the core continues to heat up. Why? Well, these high mass stars have so much mass that, they continue to heat up. Their cores continue to shrink, continue to get hotter and hotter, thus allowing carbon to fuse into heavier and heavier elements. So now the red giant phase continues. And effectively, this is when they become supergiants, SGs, supergiants. Your book refers to these as what's known as the asymptotic giant branch. You don't need to know that term necessarily. We're only worried about the red giant branch. Okay? So these become ultramassive red giants. And so what happens in this case is, you have the CNO cycle. And this is the name of the process that high mass stars fuse carbon into heavier elements all the way up until iron. Excuse me. Note that both types of stars, so all stars, use the proton-proton chain initially to create helium, right? Both stars use the proton-proton chain to fuse hydrogen into helium in their cores. It just so happens that high mass stars have enough mass to continue on to now use the CNO cycle. Low mass stars don't. So once this starts happening, then we get the multiple shell burning. Multiple shell layers, okay? And this is why those high mass stars look pretty similar to an onion, right? You have all of these layers of fusion occurring. So, multiple shell burning. Until eventually, at the very, very center, the heaviest and densest element created in the CNO cycle is iron. And if you wait long enough, iron will build up in the core. All right, so kind of all of these things happen in a red supergiant, let's say, right? So if you get enough iron built up in the core, what does that effectively do? Well, it kind of depletes the star's ability to make more light, to make more heat. In other words, the radiation pressure that's pushing out against gravity is now getting weaker and weaker because there's less stuff to fuse. So the more iron, the less stuff there is to fuse. Because remember, nature is lazy. Iron requires energy to fuse it together, right? In other words, if you were to fuse iron atoms together, it would drain energy from the star. And nature doesn't want to do that naturally. So that's why iron, it stops at iron. It continues to build up until eventually that radiation pressure drops to zero and gravity overcomes it, because gravity is always there. And that causes a massive, massive collapse. Sorry, I shouldn't say massive. A very quick collapse, known as the supernova. So now let's go down there. And now we have specifically a type 2 supernova. In other words, a core collapse. So let me put some squiggles around this, both blue and red. Okay, squiggles around the type 2 supernova, the core collapse. And at this point, there's one of two outcomes that the star can become. It can become either let's do it here, a black hole, or it can become a neutron star. Which, remember, is most likely a pulsar, a rapidly spinning neutron star. So one of these two outcomes. Which one, what's the condition for either one? Well, if at the point of supernova, the star has between 1.4 and 3 times the mass of our sun. Whoops, too many squiggles there. If it has between 1.4 and 3 times the mass of our sun, that star will become a neutron star, composed of only neutrons, much, much more massive than just a white dwarf, and much smaller too. If that star at the time of supernova has more than 3 times the mass of our sun, it becomes a black hole, right? So what was once a star emitting tons of light is now sucked up into a hole in the fabric of space-time, and nothing can escape. All right, so these 3 end results, the white dwarf, the neutron star, and the black hole, are really the only 3 fates that a star will be, right? Low-mass stars will always become a white dwarf, and then high-mass stars will either become a neutron star or a black hole. Now remember, there is a way for white dwarfs to go supernova. If somehow, say, the planetary nebula has completely dissipated and a star passing through space comes nearby the white dwarf is much more massive, and so those 2 stars become gravitationally bound, and they orbit each other. In other words, they become a binary star. And the white dwarf will then pull material off of that passing star, all off of that companion star. And if that white dwarf gets over 1.4 times the mass of the sun, remember that's the Chandrasekhar limit, then it will go type 1a supernova. So if a white dwarf were to somehow gain more mass, and it's typically done via a binary star system, right, pulling it from a companion. If it surpasses 1.4 times the mass of our sun, it'll go into a type 1a supernova and then become a pulsar, right? Or a neutron star. And this is the basic outline for stellar evolution, right? All stars start at the same place in an interstellar nebula, but there's really only one of three outcomes that a star will become, all right? There's a diagram in your book, an HR diagram to be exact, figure 13.15 that outlines this process, right? So all stars start on the main sequence somewhere, and then as soon as the hydrogen fusion stops in the core, they move off the main sequence into what's known as the red giant branch or the red giant phase, right? So notice they're moving towards the upper right part of the diagram. So their brightness is increasing, their size is increasing, and their temperatures are decreasing. And then right here, that is the helium flash. Helium flash right there. Boom, 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 boom. And that signifies the start of helium fusing into carbon. And so the star kind of bumps down and self-corrects and goes back up towards the upper right again. All right? If it's a low mass star, it'll fizzle out into a planetary nebula and a white dwarf. If it's a high mass star, it'll continue on and become a red supergiant and then go in supernova. Now, your book uses horizontal branch and the asymptotic branch. You don't need to know those terms, right? We're only worried about the red giant branch, which is right here, right? Basically all this, okay? So I hope this has given you a little bit of insight and made the general process a bit clearer for you. Again, if you have any questions, feel free, and I encourage you to send me a message, all right? Or go see CA in the tutoring center, all right? And with that, thanks for watching.